one pz left. Okay. Okay. And when we have the hybridization, the orbital has hybridization, the energy level will what? Decrease. Okay. So see, energy increased here, 2p and 2s. Okay. So when they hybridization, ps and py and s. Okay. I mean, compare with the original 2p, the energy level will decrease. Okay, and this one, pz, it doesn't attend, it doesn't mix with others, so it will keep at the same energy level. Okay, the line here is what we call energy level. Okay, energy level. Okay, so when they hybridization, do hybridization, 2p, ps and py hybridize with 2s will make the energy level diagram, energy level decrease. Okay, and the one did not attend to the hybridization, the energy will keep at the same position. OK， 有听懂吗？好。Okay, so this is what this is pz orbital, right? And the other two p, s, and py and s, they already form a plane, like a trigonal plane. Okay, and this one is what we call the left one, the pz. Okay, so we use the ethylene, okay, it's carbon and carbon, so this, okay, these are in the plane, the hydrogen can connect with them. Okay, so that's what we call, okay, it's totally, it's a 2D structure, like a plane. And this one, is tetrahedral. Okay, it's 3D. OK， 这个是立体的，好，四面体。那这个是什么？这是个平面。OK， so that's why, for example, benzene is what is plane. The structure of benzene is also as the plane. OK. Okay, so yeah, you can use this one to say that this two is pz orbital. Okay, it's pz orbital. So they may have some interaction, but it's head to head. Okay, so it will produce another single bond. Okay, sigma bonding. Okay, and this is sigma bonding, and this is side to side overlap. It will be the pi bond. Okay. Okay, so this is what the diagram of the ethylene. Okay, the ethylene. Okay, so it's P side by side, and there's another one. Okay, and there is the last one is the sp hybridization. There is only s and the ps, only one. Okay, so it's linear. For example, the carbon dioxide, okay, or alkyne,乙炔, okay. Okay, it's also alkene. Alkene is the, like for example, ethylene, alkyne. So it's also a hybrid orbital in the CO2. Okay, so same thing here. So now you have 2 sp and you still have 2p orbital left. And these 2 orbital, the energy of these 2 orbital won't change. Okay? Okay, but the hybridization, the p orbital hybridized with the 2s will decrease the energy. Okay, so it's sp hybrid. Okay. So if you use the CO2, okay, you will see like this. So you will see it's the double bond between CO to CO, okay. And for oxygen, they still have 2 lone pairs, okay, occupied in the empty orbital. Okay, so yeah, and this is the hybrid of nitrogen atom. Okay, so it means there are 3 nitrogen here. Okay, so there are two hydrogen here, sorry, and there are triple bonds. Okay, so since it's linear, so you can image. Okay, first you have to image the lone pair where the lone pair is. Okay, and actually it's the what? It's linear as well. Okay, so yeah, and in the bonding between 2 nitrogen, okay, it's linear. It's the sp hybridization as well. Okay, so yeah, it's not that difficult. Okay, so sp, as we just mentioned, there are 1s and 1p hybridized, right? Are hybridized, so you will form 2 sp orbital, and you still have 2 p orbital left. Remember? Remember like this. Like this. Okay? 1s, 1p form the 2 sp, and this 2p is from original p orbital. Okay? Okay, so yeah, go back to practices. Okay, and how about if we increase the ligand? Okay, for example, the pentachlorophosphine. Okay, penta means 5. Okay, it's the trigonal bipyramidal because these 3 chlorine, okay, are at the same plane, and there is what? In the axial position, there are 2 chlorine, right? We call this axial, and the plane here is equatorial. Okay, remember? 忘了。好 okay, equatorial means a plane. Okay, and the axial means the central axials, 中心轴，垂直的轴。Okay, axial and equatorial. Okay. Okay, so yeah, this is another PCO5. It becomes more complicated, right? Okay, because chlorine has 2p, phosphine has 2p, okay, and phosphine has 2s as well. Chlorine has 2s. Okay, so the hybridization will become more complicated. Okay, so yeah. So you can try to do the I3 minus. Okay, try to figure it out. Okay, then another one, D2sp3. Okay, D2sp3 is because S, and that S will use the d orbital. Okay, d orbital. So that's why D2 has been what? Been used in hybridization. Okay? And the D2 means 2d orbital of sulfur are used in hybridization. Okay? Okay, so yeah, for example, there is the SEF4. Okay, so just write down their Lewis structure first. Okay, write down the Lewis structure first. Then take a look. You have to take a look. You have to take care of the lone pairs on central atom. For example, here. Okay, so there's two electron, lone pair electrons. There are two lone pair electrons. Okay, so the hybridization here and the orbital at the central, the axial position, you have to round there are two lone pair and there are two lone pair downstairs, down low. Okay. So here you just only to need how to draw it. Okay, it should be fine. Okay, so here it's like describe molecule with the LOE model. Okay, first draw the Lewis structure, then determine the arrange of the electron pairs. Okay, using the VSEPR. Okay, then specify the hybrid orbitals. Okay, needed to accommodate the electron pairs, especially for lone pair. And the bonding pair, they are the option. Okay, so here, okay, this is what we say linear trigonal plane and tetrahedral trigonal bipyramidal 双三角锥. Okay, then octahedral. Okay, octahedral. Okay, so you need to know how to use the localized electron model. So go back to practice. Okay, this one is easier, right? And BF4, okay, is something like this. It's different from BF3, right? This BF4 minus is because they are extra fluoride. Okay, BF3. If now it's BF3, it should be what? It should be a trigonal pyramidal, right? But now it has one more fluoride. And fluoride has the negative charge, so that's why. This is neutral. Okay, but I got one more F minus. So that's why the total BF4 has the minus charge. Okay. Okay. And another one is SEF2. Okay. And there are two F. It means at the equatorial position there are 6 electrons. Okay. So you need to write down 3 electron pairs at the equatorial position. Okay, but at the axial position, Xe react with the fluoride. Okay? Okay? 立正型哦，很好睡哈。Okay, then the molecular orbital model. Okay, actually it's simple. Okay, 分子轨域. Okay, we call it MO. It's molecular orbitals. Okay, so since your molecule is produced by atoms, right? So the molecular orbital is the sum of atomic orbitals. For example, 1s plus 1b. Okay, you will get the bonding and anti-bonding. Okay, so this is the AO. sum of atomic orbital. Because molecular orbital is produced by the atomic orbitals. So this will make your life easier. So based on this, for example, one SA and one SB, if they are the same phase, 正对正, we call it the same phase. Then why there's a plus and minus is because when we use the wave function, on the Cartesian coordinates, there is the positive and negative, right? 我们用笛卡尔坐标的时候，只有通过原理就有正负，好。So the same phase added together will have the big molecular orbital. We call it bonding. And another one is what? Different phase. So it will produce the anti-bonding. Okay? So two atomic orbital will produce two molecular orbital. For example, here, one is bonding, one is anti-bonding. The same phase added together, you will produce a bigger orbital and more bigger. But if it's a different phase put together, they won't. Because the sign, the phase are different, so they couldn't mix up. They will repel each other, so become the two smaller one. So since we call there is a node between plus and minus, here is a node. Node, 节点, 截面. So if we use the energy diagram to represent the whole thing. So this is HA's atomic orbital, this B's atomic orbital. Then when they react to each other, there is the bonding orbital and the anti-bonding orbital. Bonding orbital, the energy level will lower than the atomic orbital. Anti-bonding orbital will higher. The energy level will higher than original atomic orbital.